Okay, welcome back. We want to review some trig. Okay, so that'll be sort of on the docket today. Okay, so this is 1.4, and we are reviewing trig. Let me get rid of this thing so I don't have to see it. Okay. Okay, so first, just some basics going between degrees and radians. I like to work in radians 99% of the time. Degrees will come up in applications, so certainly if you're in physics, you're probably going to be working in both. But the math people mainly work in radians. Okay, so first, going from degrees to radians. An example, 90 degrees. Okay. So you want to multiply by a factor, unit conversion factor. So 90 over 1 times, you want degrees in the denominator. So there are 180 degrees in pi radians. Okay. And then you just kind of multiply it out. So 90 over 180 is 1 over 2. So you end up with pi over 2. Example, negative 20 degrees. Okay, same game. So you got negative 20 over 1 times pi over 180. That'll give you negative pi over 9. Okay, great. The other direction, then, just take the reciprocal of that factor, that multiplying factor. So going from radians to degrees. Some examples. 7 pi over 6. So this time, put the 180 in the top and pi in the bottom. That'll get rid of the pi's for you. 6 times 180 is 30. 7 times 30 is 210 degrees. Okay. Trig identities I expect you to know and have memorized at this level. You need the trig functions as ratios of sides of right triangles, right? So the sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tan of theta is opposite over adjacent. Cosecant theta is just the reciprocal of sine. So it's hypotenuse over opposite. Secant theta is reciprocal of cosine. And then finally, cotan of theta is reciprocal of tan. Okay, so you should know those. Also, you should know the reciprocal identities. So sine is the same as 1 over cosecant. I mean, I don't remember what they call them, reciprocal, inverse identities, I don't know. Cosecant then must be 1 over sine. Cosine is 1 over secant. Secant then is 1 over cosine. Tan then is 1 over cotan. But also, sorry, that should be cotan there. But it's also sine over cosine. And then cotan, of course, it's 1 over tan. But then that's also cosine over sine. Okay, so you should know all of those guys by heart. You should have them memorized. And then some identities that you should definitely know. Sine squared theta plus cosine squared theta is equal to 1. And then you should be able to say, okay, on top of that, then 1 minus cosine squared theta must be sine squared theta. So any identity you can get from algebraically manipulating that original identity is kind of fair game. Also from this identity, if you divide by sine squared, you'll have 1 plus cotan squared theta equals cosecant squared theta. Then if you divide the entire thing by cosine squared theta, what do you get? Well, you get tan squared theta plus 1 equals secant squared theta. So all of those you should have definitely embedded in your brain. reference angles and evaluating. So you can evaluate pretty much any angle that you want by using the reference angles and knowing the signs of the appropriate trig functions in the particular quadrants, right? So the reference angles, first off, so we'll do a chart. And you can kind of go 2, 2, 2, and then above, radical 1 is 1, radical 2 is just radical 2, and then radical 3. Okay? And then we'll have 0 and 1 here. So this will be pi, 0, pi over 4, pi over 6 rather, pi over 4, sorry I have to smush these, pi over 3, and then this is pi over 2. I should have drawn that out a little better. Oh well. Okay. And then cosine is just the reverse of sine. You just write the same numbers but in reverse. So you start at 1, then you go radical 3 over 2, and then it's radical 2 over 2, and then it's 1/2, and then it's 0. Tan is just then sine over cosine. So it'll be 0, 1 over root 3, 1, root 3, and then undefined. Okay? So you should have that chart memorized. So you can do things like number 23, which is, or an example, evaluate all the trig functions at 225 degrees. So first I'm going to change it in the radians. Pi. 225 over 180 is the same as 5 over 6, so 5 pi over 6. So all the answers will kind of be pi over 6 based. So sine of 5 pi over 6 will be 1/2, kind of. It depends on which quadrant 5 pi over 6 is in. Okay, so here is 1 pi over 6. Here is 2 pi, 1 pi over 6, yeah. 2 pi over 6 is about right here, which is pi over 3. 3 pi over 6 is here. 4 pi over 6 is here, 5 pi over 6 is right here. In other words, we're in the second quadrant, and in this quadrant, sine is positive and cosine is negative. Okay, so let's see if we can go through all 6 of our trig functions and evaluate 5 pi over 6. Okay, so they'll follow the red chart. So sine of pi over 6 will be 1/2, and then we have to make sure it has the right sign. So yeah, it's positive. Cosine of 5 pi over 6 then is radical 3 over 2, but because it's in the second quadrant, it'll be negative. And then tan of 5 pi over 6 will be 1 over root 3, but it'll be negative because tan is negative in that quadrant. Or you can think of it as just 1/2 divided by negative root 3 over 2. A positive divided by a negative is negative. And then to get the other answers, you just take the reciprocals. Okay, and it's just that easy. Something we do a lot that we definitely need is solving trig equations. So for example, cosine of theta equals root 2 over 2. Okay, so the very, very simple trig equation. Right. So the reference angle theta is pi over 4. Right? But there are other solutions in between 0 and 2 pi. And there's an infinite number of solutions, in fact, if you include all angles possible. So in between 0 and 2 pi, though, we have pi over 4, which is right here. But cosine is also positive in the fourth quadrant. Okay, so we need to know this angle. And what is that angle? It's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. Okay. So there's another solution at 7 pi over 4. To get the infinite solutions, what you do is just kind of tack on 2 pi n, right? Because if you circle 360 degrees, you'll get back to the pi over 4. So if I just add another 2 pi to pi over 4, I'll get up there at 9 pi over 4. Okay? Or vice versa, I can go in the other direction. So that n represents the integers. So the integers, if you've forgotten, are the counting numbers, -3, -2, -1, 0, etc. Okay, and 7 pi over 4 then, plus all multiples of that. So in particular, it's anything that falls right here and anything that falls right here. Okay. If they ask, so usually they're just going to ask you for solutions in the interval from 0 to, so in the interval from 0 to 2 pi, if they ask you for that, then you could just say theta is pi over 4 and 7 pi over 4. Okay. And you don't have to worry about the infinite business. Let's look at 37. Okay. So in particular, writing up your solutions, if it's the infinity kind of case, it can be troublesome, right? Let's look at another example. Okay, so example, you have tan of theta equal to 1. What are the infinite solutions here? So where is tan of theta equal to 1? Well, that's here at pi over 4. But then there's another solution, right? There's also tan is positive in the third quadrant. So down here at 1, 2, 3, pi over 4, 4 pi over 4, which is pi, 5 pi over 4. So there's these two kind of fundamental solutions in the range from 0 to 2 pi. So theta can be pi over 4, and then to get the infinite solutions, you go 2 pi n, right? Or theta is 5 pi over 4, the infinite solution is 2 pi. You could leave your answer like that. You know, this would be all the solutions. But usually in trig, they don't teach it that way, right? What they do is kind of combine them together. Because pi over 4 and 5 pi over 4 are 180 degrees, in other words, pi radians apart. So you can actually just write all your solutions as theta equals pi over 4 plus pi n. Okay, because this pi represents 180 degree rotation, and so you could go, you know, 1 pi will give you this 5 pi over 4, and then another pi will put you back in this set, and then another pi will put you back on this set, and then another pi will put you back here, etc. Okay. Okay, so usually when you write up your solutions, you're going to be in trig class, you write them like this. But for me, I don't care. You can write them like this as two sets. It's just more cumbersome. Okay, okay, so hopefully that is kind of illuminating. Let's look at a more complicated version. So for example, cosine squared theta plus sine theta equals 1. Okay, so in this case, you have kind of a quadratic form to it. So you want to set it equal to 0 eventually, and then factor it. Okay. One of the issues, though, we need it all in terms of the same trig function. So we want like all sines or all cosines, whatever. So what you can do is use Pythagorean identities, which were those 3 identities I gave you right here. These are called the Pythagorean identities. Okay, and in particular the first one, right? So sine squared is equal to sorry, I was about to freak out. All my notes disappeared. Cosine squared, rather, is equal to, because we know what? We know cosine squared plus sine squared is 1, so therefore cosine squared must be 1 minus sine squared. Okay. So you have 1 minus sine squared theta plus sine theta equals 1. And we want to get it set equal to 0 so we can factor it. So I'm going to add the sine squared to the other side, positive sine squared, subtract sine over, and then 1 minus 1 will be 0. And then you treat it like a quadratic. Okay? You're going to factor it. Here we can factor a sine theta, and we'll have sine theta minus 1. And then you set each part equal to 0. Okay. So in the first case, if we were going after infinite solutions, sine is equal to 0 when theta is 0 and when theta is pi. So theta is 0 plus 2 pi n. But also when theta is equal to pi plus 2 pi n. And then if you're clever enough, you can combine these two into just saying that theta is 2 pi n, right? Or rather pi n, not 2 pi n. So 0 basically plus pi n, which will be pi n. On the other hand, if we have sine of theta equaling 1, that's going to happen when theta is theta is what? So it's going to happen at pi over 4. Or sorry, not pi over 4, but pi over 2. And then that's it. Because if 3 pi over 2, it's negative 1. Right? So it's only going to happen at pi over 2. And then the infinite solutions just add in 2 pi n. Okay. Okay. So our set of infinite solutions is this. If they just want the answers in the interval from 0 to 2 pi, then what? Well, sorry, I have a brain fart. Then you just use these formulas to get all of those. So theta will equal n times pi. So 0 times pi is 0. 1 times pi is pi. 2 times pi is 2 pi. 3 times pi, it goes out of the range. Then from the other one, we have pi over 2. And then plus another 2 pi would put me at 5 pi over 2. Sorry. That goes out of the range, though. Yeah, that's out of the range. So it's just those 4 solutions. Okay. Graphing these things, I kind of talked a little bit about it in the transformation section. I just want to look at maybe one example. So let's take an example. Y is 3 sine of x over 2. Okay. So first off, vertical, there's none. Stretch and shrinks. So the amplitude, in other words, the amplitude is 3. So it goes up 3 and then down 3. And then the period, one full period, is in between 0 and 2 pi. So it's going to stretch it, right? I didn't mean to write 2x and not 2 pi. So if you multiply by 2 all the way through, you get 4 pi, so it stretched it. And then I want to cut the period into 4 parts. So I'll be going by pi's on the x-axis. Okay? 1 pi, 2 pi, 3 pi, 4 pi. I want one full period. The amplitude is 3. So it's going up to 3, 0. And then that would be one period, and it goes on forever. Okay. So that's the big and the small of it. Let's see if there's anything crazy in WebAssign. Oh, wait, I still have... Seems like I need the inverses. That's the next section. Okay, let me see if there's anything crazy in WebAssign. sine of theta is 1/2. So if sine of theta is the ratio of sides of a right triangle, the opposite side should be 1, the hypotenuse should be 2. So that would be this guy here that I just sort of borrowed. And then evaluate all of them. So you're going to have to solve for the third side, and then these are all just kind of trig problems. Maybe I should do, these are in the interval, so they're not asking for infinite solutions, just want the interval. That's one that we did. That's one that we did. Graphing. This is a shift. This will be a horizontal shift by pi over 5. This will be a horizontal shift to negative pi over 5, and then vertical stretch of 8. Oh, okay, so I think that's good enough. We'll let you go. Try the homework. If you have any questions, see me in my office hours. Okay, see you next time.